Hi, everyone. Hope you enjoyed the energy chapter so far. Hopefully, the homework wasn't too horrifying. Uh, Take a little look, or I want to spend a little bit more time with forces and potential energy. Nothing too profound here. But remember again that the big idea in this chapter is that you can think about force as being the negative derivative of potential energy with respect to distance. And so if you've got a graph of a spring, remember the force looks like this, the potential energy curve would look like this. As you displace it this way, you've got a positive slope du dx, which means the force is in the negative direction. It's trying to restore it back towards equilibrium. Over here, the slope is positive du dx, and over here, then, you've got a positive force, which is again trying to push it back towards equilibrium. I should put negative there, but you can see by the direction. How far an object gets as it oscillates back and forth around this depends on its total amount of energy. So take a quick look at this. Remember, the total amount of energy involved is just mechanical energy. It's the sum of kinetic and potential energy. And that should be constant as long as no work, no external work, is adding or removing energy from the system. So if the total energy of this system is given by this value right here, I know this is kind of abstract, what's going to happen here? This thing can go up to a maximum position of here and here, but it can go no further. At this point right here, all of its energy, since the total energy is equal to this line, and it has to be the sum of these two, at this point the potential energy is a max. And what's happened to the kinetic energy? The kinetic energy is zero at this point, and kinetic energy is zero at this point over here. It can't go beyond this point because then the kinetic energy would have to be negative because the potential energy would be even larger than this. And down here, it has zero potential energy, and all of its energy is in the form of kinetic. And so it would oscillate between these 2 points. It could never escape that. And so these are what are often times called turning points. It has to turn around here and return. It can't go beyond these two limits. This has some interesting effects. So take a look at this graph here. Here's a graph of potential energy versus distance. And if the total energy in this case is 5 joules, and this is a graph of potential energy, the furthest it can get close here is x1. Why? Beyond that, the potential energy goes above 5. At this point right here, the kinetic energy has to be 0. All of it's in the form of potential. I'm going to give you just another quick example here. At this point right here, the potential energy is 3. What's the kinetic energy at this point? Well, it has to be 2 joules because we know the sum of those has to remain constant. Over here, it's got even less potential. The kinetic energy at this point would be 4. And over here, the kinetic energy would have to be 5, all of it. Over here, the kinetic energy would be 1 joule anywhere along this point right here. This here is the negative derivative of this slope. And it kind of shows you, and I like this graph, it shows you what's happening. As it approaches this point right here, the force is positive. In other words, it's pushing the object away, and that's slowing it down, and it never gets beyond x1. Right here, it just can't make it. And there's some other interesting points I just want to show you here. x2 is a very interesting point. x2, the force is 0, but what's this graph mean? Well, if you go on this side, the force is positive, which means it's pushing you back towards x2. What happens if you're on this side? Well, the force is negative, which means it's pushing you back towards x2 here. This point right here is a point of stable equilibrium. If you move in either direction, it tends to want to return back to this point. Over here, the force is also 0 at x3. But here you've got a point of unstable equilibrium. If you move even slightly this way, we've got a negative force that pushes you even further away. If you move a little bit over on this side, you've got a positive force that pushes you away as well. So this is a point of unstable equilibrium. It's equilibrium because the forces are 0 at these points, but this one's stable, this one's unstable. What about x4? If you think about it for a brief moment, you should discover that x4 is a point of stable equilibrium as well. Finally, I should mention this point right out here where the force is 0 along here. What is this area? Well, here, if you move away from this point either that way, the force is still 0. And so this is also a point of equilibrium. This was stable, unstable, stable, and this is called neutral equilibrium, where motion in either direction doesn't change your equilibrium whatsoever. If we talked about this, I just did this right here. You can talk about stable and unstable equilibriums. If the total energy is blue here, so you say, for example, your total energy is 4.5 joules, your object is free to leave the system. If your total energy is 3 joules, you're trapped somewhere between these 2 points. You can't travel any further. You can move around this point and back, but you can't go any further. If your total energy is 1 joule, you are trapped between these 2 points. You're free to move anywhere between these, but you can't go beyond that. And so this happens a lot in, for example, chemical molecules, where you end up with these kind of potential energy graphs between the 2 atoms, and they'll jiggle about that point of equilibrium, but they're usually trapped unless you add enough activation energy to actually separate them. Talking a little bit about energy, work transfers energy in and out of our system. It changes the total mechanical energy, which means it changes the kinetic and potential. If there's work entering the system, that means the overall energy of the system increases. In this case, the external work could be you lifting the bowling ball off the ground. Now it gains potential. Kinetic may or may not change, but definitely then this is increasing. Why? Because energy has been added to our system. You might remember those kind of things from last chapter. Floor block system, you can actually do some calculations here. In this case, there's thermal energy being generated. Thermal energy is a type of work. So work can equal the change in mechanical. It can also equal the change in thermal energy. Last year, we used to call this just E-dis. So, yeah, you can end up transferring some of the energy into E-dis in the system. Non-conservative forces, conservative forces, we talked about a few of those. And let's move on a little bit. Conservation of energy. So in a roller coaster is a classic example of this. So the work equals the change in energy, which is the change mechanical plus thermal energy, plus it could be the internal energy of the system. But if it's isolated, that total amount of energy can't change. So what do we have here? Assuming there's no friction, we shouldn't have too much change in thermal energy. And so the kinetic energy plus the gravitational potential energy should stay constant. And so what's going to happen here? On the first hill, you've got some initial gravitational potential energy, but no kinetic. On the second hill, you're going to be back down to velocity 0. Don't ask me how you're going to make it over there. Or sorry, not 0. It's just some initial velocity. You're back to the same initial velocity as you had in the first hill here. And down here, you're going to have a velocity that's going to be greater than the initial velocity. And then at point C, all of your energy is going to be converted into kinetic. All of the initial gravitational and kinetic. I don't know if it's worthwhile. This is on defining where your GP is set to 0 point is at. Okay. Just to make it simple, let's make gravity 10 meters per second squared. In that case, how much work is done by gravity as it falls down? Well, it'd be the force of gravity on the book, 20 newtons, times the distance it falls, 8.5, which gives us 170 joules. Positive because gravity is acting in the same direction as the displacement. What's the change of potential energy? Well, we know work is equal to the negative change of potential. It's going to be negative 170 joules. What was the potential energy at 10 meters? Well, that would be 2 times 10 times 10, or 200 joules. The potential energy at 1.5 meters would be 30 joules. And that's our change in potential is right here as it goes from one point to another. Now, what happens if the initial potential is defined as 100 joules up here? Now, so that means the potential energy here is 100 joules. That means our height equals 0 point has to be, oh gosh, let's see, 20, has to be 5 meters below where the book is set. So 5 meters below this point is where we're setting GP equals 0. That would give us this initial 100 if I'm doing my math right. So what happens here? What's the work done by gravity? It's still going to be 170 joules because it's still moving through the same displacement, same force. The change of potential is going to still be this. What's the potential energy going to be here? If I start out with 100 joules and I lose 170, my GPE down here is going to be negative 70 joules. Don't panic. It just means you're now 3.5 meters below our point where we set the potential energy to 0. If I'm doing my math right again. And so we end up with a negative GPE. This one real quick here. Pendulum bobs, we've done a little bit of this before. How do you calculate the speed when it's at the bottom here? Well, we need to figure out the change in GPE. And so if you draw this line over here, you'll discover, of course, that this side of this right triangle is going to be L cosine, of theta, which means what's our change in height over here? Delta H then is going to be L minus L cosine theta. Or you could write it as L times 1 minus cosine theta. And so then what's the expression for the speed at the bottom? It would just be the initial kinetic energy, 1/2, I am too close to my bottom of my screen, sorry. 1/2 mv0 squared plus our change in gravitational potential, mg L 1 minus cosine theta, would equal our final kinetic energy, 1/2 mv final squared. I could have also written this as the change in potential equals the change in kinetic, but you get the idea. And this expression, you could solve it. Notice that mass cancels. You could simplify a little bit and actually solve for v final. And you could use this equation to figure out how high it's going to go up vertically. If you convert all of its initial kinetic energy into GP, you can figure out the height and the angle, and a few other pieces. All right, ski jumper. A 60 kilogram skier starts at the top at a height of 20 meters above the edge of the top of the ski ramp, leaves the ramp with an angle that. What's the maximum height? And you might say, oh, wait a second, it should go up to exactly 20 meters above where it started. But please realize at this point here, we still have a horizontal component of the velocity that's equal to what it was over here. Doing the math on this one just real quick, we know the energy is equal to the potential plus kinetic. Shouldn't have a delta in front of those, sorry. In this case, if you do that real quick, you'll discover that if the skier goes through a distance of 20 meters, they should be going at 19.8 meters per second squared. And if we break that into its vertical and horizontal components, we'll discover the horizontal component is 17.5. I won't bother with the vertical, which means it has to be 17.5 over here. Solving this now, the total energy of the system is the initial gravitational potential energy, 60 times 9.8 times 20, equals the potential energy at this point right over here, which is going to be the mass of the skier times 9.8 times the height, plus the kinetic energy they have at that point, which is 1/2 times the mass of the skier times this velocity, that horizontal component of the velocity squared. Remember, for a projectile, horizontal velocity remains constant, but at this top point right here, the vertical velocity drops to 0. Mass cancels out, and then if you solve this, you'll discover that height must be 4.41 meters. What happens if the skier puts a backpack on that's 10 kilograms? What's that going to do to this change of the height? The answer is nothing, because remember, the mass of the skier and or backpack cancels out. This one we did a problem like this last year in honors physics. In this case, a diver steps off the diving board up here at some height, which in this case is 3 meters. And the water does work on them. And the question is, how far below the water do they stop? So in this case, the total energy of the system has to remain constant, and it has to equal the total mechanical energy of the system. The only challenge on this one is where you define your 0 point. I'm going to define 0 at the height of the water. So what does that mean? The initial energy of the system is just going to be the mass of the diver times gravity times the height above that point, which is 3. And the final kinetic energy, hold on here. I forgot to put in this fact here. The water has a resistive force of this on it. So we got a little bit more change, or a little more interesting problem here. Work is equal to the change in energy of the system, which means it's equal to the change in the kinetic plus the change in the potential. In this case, the work done by the water is negative 520, and that's going to equal the change in kinetic. Well, interestingly enough, the final initial kinetic energy is the same, so that's going to be 0, plus the change in the gravitational potential energy. Well, that's going to be the final minus the initial. The final is going to be the mass of our person 95 times 9.8 times negative d, because I define my 0 point is here. They're d below that point, minus 95 times 9.8 times 3 meters above is where they start. And if you solve this, you'll get d. Let's see here. And I think you get about 2.50 meters below the water, which, okay, that makes sense, I guess. All right, moving on. This case, a rocket, you've got a small rocket. It's going for a change of height of 29 meters, and the rocket engine does 425 joules of work on it. This one's a little bit faster. Work equals the change energy, which is a change of each one of those. Plugging in our numbers, our change in gravitational potential is just, this is delta H, 29 meters, equals that plus the change in kinetic energy. Since the initial velocity is 0, we just end up with final kinetic energy minus initial kinetic energy. We just end up with that, and if you calculate it, the rocket should be going about 60.7 meters per second. Doesn't matter which direction it's going, because we're just talking about the total energy. And so you can calculate this even though we can't exactly calculate direction. Another quick one. Sorry, the box is showing up beforehand. You've got one of these potential energy graphs, and you've got a few points on it. If the mass is that, and at x equals 0, we're given that the velocity, so when x is equal to 0, we're given the velocity is this. The question is, what's the velocity when it's over here? Solving this one, first of all, figuring out the total energy at x equals 0. We know the potential energy is 9.35. That's given here. The potential, or the kinetic energy, 1/2 mv squared is this, because they gave us the velocity up on top. We can figure out the total energy is 13.6 joules, and that's got to stay constant as long as there's no energy entering or exiting our system. What's it at x equals 2? Well, at x equals 2, we know the the potential energy in this case is 4.16. That has, along with the kinetic, has to equal the same total energy. Plugging in the numbers and solving, we end up with the velocity there is now 3.43, larger than it was beginning. Why? Because we've converted some of the potential energy into kinetic energy. Last topic in this chapter is power. Remember, power is the change in potential energy or any type of energy over time, measured in watts. That's equivalent to joules per second. You can also calculate the energy as is the integral of power dot dt if it varies with time. One common unit of power is the kilowatt, but just a quick warning on it. electric bills each month are actually billed in kilowatt hours, but that's actually power times time, so it's a unit of energy. 1 kilowatt hour is about 3.6 megajoules. Just a quick reminder, and this is just a reminder here, work is force, oops, sorry, that should be an X. Force, work is force times distance over time, which means you could rewrite it as force times dx dt, or force times velocity. That's a special case of power. Quick example of this one, the 2012 Buick sort of minivan had an engine power output of that and a drag coefficient roughly given by this equation. What's its maximum possible speed, ignoring all other losses of energy? Well, you know that power special case is equal to force times velocity. Plugging it in, again, remember that the old-fashioned unit of horsepower, 1 horsepower is equal to 746 watts. That's the conversion factor. So converting this now into watts on this side, and then our force is this, and our velocity is here, and what we're trying to solve is that velocity. You end up with this. Plugging it into your Inspire, you'll discover the theoretical maximum speed is about 70 miles per hour. That means that obviously my equation here for the drag is probably too large. I think the van could go much faster than 70. Two quick examples from your homework for tonight. This is number 79. Apparently, the size of a crater is roughly proportional to the power of the explosion raised to the 1/3 power. And an explosion of 1 megaton leaves a crater with a roughly 1 kilometer diameter. Beneath Lake Huron in Michigan, there appears to be an ancient impact crater that's 50 kilometers in diameter. What's the kinetic energy of the impact? All right, so first of all, we know that power to the raised to the 1/3 power is roughly proportional to the diameter, where I'm using alpha here as the proportional symbol. If that's true, I can do the nice little ratio here. Power 1 raised to the 1/3 over power 2 raised to the 1/3 should be equal to diameter 1 over diameter 2. So solving part A. So for that 50 kilometer crater, I know that 1 megaton produces a 1 kilometer one. So what's the power required to produce this? And you end up, of course, with an expression that looks like this. And solving it, you'll end up with the crater underneath Lake Huron must have been roughly an explosion of 125,000 megatons, or 125 gigaton explosion. That's pretty big. How many equivalents to Hiroshima is that? Well, just doing a couple of factor label ones. First of all, converting megatons into kilotons, using this expression, factor label, and then 1 Hiroshima explosion was equal to that many kilotons, you'll discover that the explosion was roughly 9 million Hiroshima explosions, actually closer to 10 million Hiroshima explosions. That's big. And then finally, this question number 34, which I apologize is cut off in your homework, so I wanted to do this one. The question is this. Two children are trying a game which they're trying to hit a small box on the floor with a marble fired from a spring. The question is, okay, so this is 2.2. They compress it 1.1 centimeters, but it falls short, 27 centimeters short of this. And the question is then, how much should they have compressed it so they hit it? So a quick note on this one, the horizontal distance the projectile travels is directly related to its horizontal velocity, which in this case is all of its velocity as it leaves here. In this case, it travels 27 centimeters short of that box, so it travels this far. Therefore, to make it go to the 2.2, we need to increase it by this ratio. We need to make its velocity 1.14 times as great, which will give us 1.14 times as much distance. Doing the math on this case, it's EP equals KE. Solving this, to make to make the velocity 1.14 times larger, we need to make the distance we compress it 1.14 times larger. Why? Because x squared is directly related to v squared. Doing our numbers then, if we need to make the 1.10 centimeters that was initially compressed 1.14 times larger, in other words, we need to compress it about 1.25 centimeters. All right. With that, you should be set to do your homework. Good luck. Ask me any questions. There's office hours as well. So we'll see you soon. Bye.